Hello, everybody. In section 6.3, we are going to find the volume of solids of revolution like before, but using this new method called shell method. The shell method is based on, of course, shells, not discs or washers. So let's see if we can get this done. All right, let's learn the shell method from section 6.3. And we will get started. All right, so the shell method, sometimes called the cylindrical shells, it's based on something very, it's sort of similar, but we are dividing the solid of revolution in quite a different way from intuitive slicing to get shells. To slicing to get disc or washer. And so we kind of have to think of this in different ways. But first, let's review the method we learned so far. Okay, so here's an example. Right, so let's say you have this parabola, upside down parabola. Y is negative x squared plus 4. So this is 4, and this point is 2. The x-intercept is 2, and the y-intercept is 4. And let's rotate this about the y-axis. So rotate about or one on the y-axis, and you remember you eventually will get something like that, of course, right? But each disk, well, we have to figure this out, x in terms of y, because we are revolving about the y-axis, right? Using the disk method, when you revolve about the y-axis, you have to, for each y, find x in terms of y. So if y is equal to negative x squared plus 4, and if you have to solve this for x, well, x squared is 4 minus y, and so x is, and by the way, here you can see that x is positive. We're going in this direction. We are not considering where x is negative. So if x is non-negative, then this will give rise to the expression x is the square root, positive square root of 4 minus y, or 4 minus y to the 1/2 power. Okay, no problem here. So by using the disk method, we can calculate the volume of this solid of revolution. That looks like the shell, and it's going to be, let's see, the volume is pi times the integral. Now remember, y goes from 0 to 4, right? And then you have the function squared dy. And of course, that's pretty simple. It's pi times the integral from 0 to 4 of 4 minus y dy. And so that's pi 4y minus y squared over 2, going from 0 to 4. That's pi times 16 minus, of course, 16 minus 2, that's 8. Okay, so that's going to be 8 pi. Now we've done this before, except I think the first time we did this, we revolved another function with respect to about the x-axis. Okay, so that is what we did before. But now here's a tricky part. We slice this way, right? Which is basically the way we sliced this was in the way perpendicular to the axis of rotation. Axis of rotation or axis of revolution. In this case, was the y-axis, and then we sliced everything so that each slice was perpendicular to that axis. In the shell method, we're going to do something very, very different. So let me go ahead and copy that the graph that I had before. Okay, so here is another way to divide this solid into smaller pieces. Okay, and again, we did slicing first, so each slice was like a disc. But here's another way to partition the solid. Okay, so instead, so remember we revolve this about the y-axis. Okay, but we take the same solid, and this time we're going to pick a point. So this was from 0 to 2. Let's pick a point any point x between 0 and 2. All right. So what corresponds to this? If you take this line here, or line segment from 0 to, and this is, fx, right? Y is equal to f of x. I didn't solve this for x because we are not dividing this by slicing with respect to, for each y. This time I'm taking this x between 0 and 2, and then consider this line segment, okay? And what happens if you revolve the that line segment with respect to or on or about the y-axis? You will get something that looks like a disc, or not a disc, a shell, a cylindrical shell. Now let me draw a picture here. See, this is the entire solid I'm talking about, okay? And here's your axis of revolution. And now if I take this x, or the maybe like the bar graph or the line segment corresponding to this x, and if you revolve this, what you'll end up with is this blue shell that looks like this. See that? Okay, and so that's corresponding to that blue x here. Let's use another color, maybe something bright. And if I take this x that's even closer to 2, that's going to correspond to that. If I revolve that green line segment about the y-axis, you will get another cylindrical shell that looks like this. Okay, that's going to be wider but shorter. Okay, and you can do this for every x. In fact, if you take every x between 0 and 2, you can divide this entire solid into a bunch of shells. Okay, maybe I can do another one. Maybe this one here, if I take this x, it's very tall, so that's going to correspond to that, but it's going to, the radius is going to be smaller, and so that's the shell I'm talking about. So each shell, let's say each shell is going to look like this. Okay, now again, this is very different from slices, right? But it is another way to partition, divide up this big, the solid into smaller things, right? Not discs, not washers, but shells. So each shell is going to look like this. It's, what does it look like? Well, it's like, these cylindrical shells. All right, let's try to examine this. The height is fx. That's defined as y is equal to f of x. And then what's the radius here? Well, radius is exactly the distance from 0 to x, which is called x, right? Okay, and then the thickness is, of course, what we call delta x. That thickness here of the shell, we can call it delta x. And if we use a partition that's not evenly distributed, or if it's not a regular partition, we can call it the ith subinterval. So the length of the ith subinterval as you partition this interval from 0 to 2, we used to do that too. Okay, now if we can find the volume of this thin cylindrical shell, and then you can integrate from 0 to 2, then we will get the entire solid covered. Okay, so this is quite a different way than the disk method, but we can do it this way. We can find the volume of this entire solid by adding up the volumes of a bunch of these shells, each corresponding to one particular x value between 0 and 2. So you integrate with respect to x from 0 to 2, right? Even though you are rotating this with respect to or about the y-axis, right? So the shell method is going to allow you to rotate about the y-axis, and you can still integrate with respect to x. All right, so how do you find the volume of this thing? Well, let's open this up. Okay, that's the key here. If you open this up, it'll be a rectangular sheet like this, a thin sheet. Okay, so in other words, what you're doing is you're making a little cut like right here, right? And you open this up, and then the thickness, of course, is delta xi, right? And then the height is f of x as before. Now, what's the length? What's the width of this thickness if you open this up? Well, that's going to be, remember the radius is x, right? And this corresponds to the circumference of that circle. That's 2 pi x. All right, so the each volume, we can call this the delta VI, if you like. Okay, that's the volume of the ith shell, where I is the index for the partitioning and the subintervals. So the volume of this ith thing, the partitioned or the ith cylindrical shell, is going to be basically the volume of multiplying these 3 dimensions. So it'll be 2 pi x, which is the circumference, times the height times delta xi, right? So add them up, and then you have an accumulation of the volumes of these shells. And of course, that sum is, if you take the limit as n approaches infinity, is going to give you the definition of the definite integral. So the volume is going to be the integral as x goes from 0, well, a to b, well, yeah, a to b. And in this case, I'm calling this a and b here like this, right? Okay, so it's 2 pi x, well, 2 pi can be taken outside. And then you have x, f of x, well, delta x becomes dx. And so that's the volume formula using the shell method. So the shell method, so not, yeah, shell method. Or you can call this the method of cylindrical shells. But the shell method volume is going to look like this. Now notice here, I am taking the integral with respect to the x-axis, but because of the way the shells are oriented, this is a solid obtained by revolving a certain region about or on the y-axis. So using the shell method, if you revolve about the y-axis, you use an integral with respect to x. And conversely, if you take a function and revolve it on the x-axis, then you take the integral with respect to the y as the variable. Okay, so let's go back and look at this thing here from 0 to 2. And this is y is equal to negative x squared plus 4. Now, remember, the answer was obtained using the disk method, and we know the answer to be 8 pi, right? This thing here. Okay, the volume is 8 pi. But now let's use this. Let's use the shell method to calculate this, and hopefully we get the same answer of 8 pi. All right, so the volume is going to be, remember, it's going to be 2 pi times the integral from 0 to 2. Now we do this. See, the first time using the disk method, we had to take the integral with respect to y, right? We had to, in fact, solve the function f of x in terms of x, x as a function of y. I don't have to do it this time. This time it's 2 pi times x times the function, okay, because this function actually gives you the height or the length of the, the shell, vertical shell, right? So it's x times f of x dx, right? So what you're integrating actually is 2 pi x fx. So this will be 2 pi integral from 0 to 2 of negative x cubed plus 4x. That's what you're integrating. And so that's 2 pi, and then negative x to the 4th divided by 4 plus the antiderivative of 4x, which is 2x squared. You integrate from 0 to 2, and 2 pi is still in front. Negative, now what's 2 to the 4th? That's 16. 16 over 4 is 4. And then 2 squared is 4. 4 times 2 is 8. That's the first of the top part of the fundamental theorem of calculus formula. And then when you plug in 0, of course, you get 0 minus 0. All right, so this is, of course, 2 pi times 4. And are you happy to find the answer, which is consistent with my first method? Yes. 8 pi is the answer to that. Okay, so that is called the shell method, right? Again, let's make sure we understand this. The shell method is based on this, adding the volumes of these small and tiny shells, and the way to find the volume of one of those shells is to open this up. Just make a cut here and open this up to make it into a flat sheet whose thickness is, delta xi, but then the height is, the length of the shell is f of x, and then the circumference, which becomes the horizontal length of this piece, is 2 pi times x, because it's 2 pi times the radius. Okay, so this is what you're trying to integrate, 2 pi x times f of x. If you remember this, if you remember where this thing came from, you will not have a hard time remembering this formula. And in fact, even if you forget the shell method formula, if you can remember the process, you can probably come up with this formula yourself on the spot. All right, let's do an example or two. Okay, let's start with something very simple. All right, and that is, well, you'll see. Okay, so I'm going to take this from 0 to r, and I will just do a constant function. Fx is equal to h, okay, from 0 to r. If I rotate this or revolve this about the y-axis, what do you get? Of course, you just get a very simple cylinder, okay? What is the volume of the cylinder of radius r and height h? We know this from geometry as pi times r squared times the height, right? Okay, let's verify that using the shell method. All right, remember the shell method has 2 pi in front and then integral from 0 to r. And here I am going to remember, I am going to use the integral with respect to x because I am revolving about the y-axis. All right, so 2 pi times x times f of x. Now f of x is simply h. This is a constant function, okay? And so that's what I am going to do. And so this is 2 pi h, and then if I integrate x, you have x squared over 2, going from 0 to r. And of course, 2's will cancel. You have pi h, and then r squared, which is of course pi r squared h. And that is the formula that what you learned when you were a toddler or kindergarten student. All right, so that's a nice example. And I am going to go into the next segment of this section video to do a couple more examples.